করতে হবে না এগুলো?
থাক।
Short video. Yeah. Okay. So in the last lecture we were talking about classification of folds. We were talking about how they can be subdivided into based on interlim angle, axial plane dips, and plunges of folds. Now here we start on a slightly different, and we have talked also about how I suggested stereographic projections and how you can find out different parameters of a fold given some input data. Now here we talk about an interesting finding, and that is relevant to some sedimentary rocks. This relates to deformation, not only folds, it's also related to forms. How folding, we will emphasize this here, how folding inverts stratigraphic sequences. So we know that in sedimentary rocks, if it is a right side up section, and this you can find out by a host of sedimentary structures like graded bedding, current bedding, asymptotic bottom, truncated top, mud cracks, certain types of ripple marks which you can read out, which you can find out from the internet. There are ways in which a sedimentary rock can, if you see a rock on a hill, whether the rock is right side up, that means whether as you go up you get younger rocks, whether this is valid or this is not valid, based on certain criteria. Some of the criteria, as I just now said, graded bedding, current bedding, ripple marks, mud cracks. There are different ways you can do. You can also do it from some igneous rocks. Say for example, in some igneous rocks with lava flows, what happens when a lava is in place, then gas bubbles, gas which are trapped in the magmas, they try to move up towards a zone of low pressure atmosphere. So what happens, the cracks widen up at the top, so you get cone-shaped air gaps, which are later filled up by something else much later. But they also tell you this widening of the amygdaloidal structures, as they're called, amygdules, widening of the amygdala, forming some sort of a bell, an inverted bell-like structure. And those can be used to find out stratigraphic successions. But sometimes these successions can be inverted by both folding and folding. Here I will tell you how they are done based on folding. Now let's say you have a sedimentary rock with this four strata. This is old and this is young. This is old and this is young. The lowermost layer is older and the younger layer is younger. So this is old and this is young. This is a right side up sedimentary. So in this we erase it and we take two layers and write young and old. Meaning this is our marker horizon and this is younger, so it's right side up. So younger rocks occur like this. Now what happens when you fold it sometimes? Sometimes it's not necessary to know how, but what happens is when you apply stress on these rocks, so instead of this they generate a fold structure which is like this. A fold structure like this, and this of course you can see is the trace of the axial plane. Is the trace. Let's say this is a vertical section. Let's imagine this is a vertical section. So the axial plane is inclined. If this is a vertical plane, then this is the horizontal line, and therefore this is the dip of the axial plane. And if I keep the stratigraphy here, then it's old and young. In between, it is between young and old. And if you follow this, then this is young and this is old. What has happened? That's very interesting. What has happened? Here, it was a right side up geologic section. As you fold it, the section is inverted. That means now your younger sediments lie below the older sediments. Lie below the older sediments. So what happens? This is called a normal limb. Normal limb. Why? Because that stratigraphic succession is normal. And this is called an inverted limb. Why? Because here the stratigraphic succession is inverted. Now you see the important point here. If you extend this to this horizontal plane, and you see this one was the dip of the axial plane theta, and now this, if you draw another tangent here, so now you can see this angle is alpha. That means the inverted limb has a larger dip than the dip of the axial plane. So that is how you find out how a limb is become inverted. So what has happened here, either if you see sedimentary structure, say for example, let me draw some current bedding here. This is how current bedding would look, right? This is how current bedding would look, and here the current bedding would look like this. Here the current bedding would look like this. So what happens? This is the eroded top, and this is the asymptotic bottom. Have you understood? This is the truncated top, and this is the asymptotic bottom. Here, this is the truncated top, this is the asymptotic bottom. So there has been an inversion of the stratigraphy, because this layer, if I take this layer has been folded by more than 90 degree. More than 90 degree dip. Otherwise, if you had this layer and if you folded it, here you can see, here for example, old, young, old, young. So what happens? In both the limbs are normal stratigraphic sequences. Normal stratigraphic sequences. Do you see? But when you tilt this layer more than verticality, then you start inverting the young and old. So if your axial plane dips more than 90 degrees and the inverted limb has a dip amount more than the dip of the axial plane, then that limb is inverted. An extreme case of this inversion is this. And this you can see is a recumbent fold. You see, this is a recumbent fold. But this is the axial plane. This fold, this plane is an axial plane. And here you see, in this it is, here it is young, old. Here it is young, old. So this is what causes the fold to become an inverted fold, in which one of the limb will definitely have a stratigraphic inversion. Have you understood? So please remember that in the inverted limb, the normal stratigraphic sequence is reversed. An extreme case is where you have recumbent folds, where it's completely reversed. So you can see the current beddings here are just opposite to what is the current bedding. This is the normal sequence. Old, young, old, young. Truncated top, asymptotic bottom. Truncated top, asymptotic bottom. Here it's reversed. Truncated top below, asymptotic bottom above. It's all reversed. So that is one way, one of the ways in which asymptotic, in which case inversion occurs. Now, we talk of some sort of a different fold classification. Now, say I take a fold like this, and this is the third dimension on the ground surface, and you have a fold like this. So now, this is what is called, this geometry, where it is where the curvature of the fold is convex upwards. This is called an antiform. This is called an antiform. This is called this is called an antiform. But say for example here, like this. Now you see, here there is a difference. Here this is an antiform. What is an antiform? The two limbs are dipping away from each other. The dip here is this way and the dip here is this way. The two limbs dip away from each other. Okay? And this is convex upwards. That's called an antiform. It is completely based on the form of the fold. This is different from what is called an anticline. There is what is called an anticline. Now, here it's slightly different. Here, for example, the beds dip away from each other. That's sure. It's the same as an antiform. Absolutely same as an antiform. And the younger rocks, this is the horizontal plane, remember? This is the horizontal plane. And the younger rocks with dips this way and dips this way, younger rocks, occur to the flank of the fold. And the older rocks are exposed at the core of the fold. Are exposed at the core of the fold. So what happens? What is the difference in antiform and an anticline? In an anticline is essential antiform. Is essentially an antiform. But with younger rocks in the flanks and the older rocks at the core. That is the important part. So, if you are, for example, walking this way, you will have to walk from younger rocks and then on to the older rocks, and then once again you will get younger rocks on either side. So the oldest rock is exposed near the hinge of the fold, or at the core of an anticline. It's called the core of an anticline. Now remember one thing, you don't have just a single antiform. You may have rare instances, but normally your antiforms and the corresponding one. So once again, just before we go into this is an antiform based only on form. The age distribution or the stratigraphy is not important. Here, for an anticline, the stratigraphy is important. That the younger rocks at the flanks and the older rocks at the core. And the limbs dip away from each other. As you can see, if you walk this way, then you're walking parallel to the dip. If this is the direction of the dip, so if you're walking this way, if you walk along the dip direction, then you will have younger rocks, older rocks, and again younger rocks. So that is how the difference is between anticline and an antiform. Antiform is purely geometrical. Anticline is geometry ingrained with stratigraphy. Now, if you have a fold, there has to be a counterpart here. Do you see? This is the part that I have drawn here. But it will have, because it's a sinusoidal wave, it will have the opposite also. So you will have this type of structures alongside also. So let's look at that. So you know what is an anticline. An anticline is essentially an antiform where the older rocks occur, progressively older rocks occur at the core of an anticline. That's what is at the core of an antiform. That's what is exactly an anticline. Now we are talking of a part here. So now, look at the dips. This is the structure of a synform. So this is the structure of a synform. Again, like an antiform, is purely based on geometry. In this, the dip of the beds point towards each other. Remember, in the antiform, they were dipping away from each other. Here, they are dipping in the same direction. Opposite direction, but in the same direction. So this is what is called a synform, and it is convex downwards rather than convex upwards as in an antiform. So there are two differences. One is here the dips are point towards each other, and it's convex downwards, opposite of an antiform. So now, like synform, we will have something like a syncline. So how will that work? So this is young and this is old. That's the normal sequence. That's the normal sequence. So here you will have older rocks, here you will have older rocks, and here you will have younger rocks. And the dip is towards each other. So this is what is called a syncline. Remember, this is the axial plane of the fold. This is the axial plane of the fold. Same here. This is the axial plane of the fold. Divide the fold into two equal halves. Right? So here what you see is a syncline is essentially a synform. Have you understood? What I told you what is a synform? The two limbs dip towards each other and it is convex downwards. Right? A layer or a strata or whatever it is. Syncline is essentially a synform where the flanks are consisting of older rocks and the core exposes the younger rocks. So the core of the syncline exposes the younger rocks, and the flanks, as you move away from the flanks, so you get, if you move in the direction of the dip, and you are standing here, and you're moving in this direction. So from old, progressively young, and again old. So the flanks are older rocks, and the cores are younger rocks. That is what it's all about. Right? Synform and synclines. Now we talk of something else. I say there is something called an antiformal syncline. Say I tell you this is an antiformal syncline. What is it? So it is essentially, as this says, it has an antiform. So it has the structure of an antiform. So if we draw this, so it will have the structure of an antiform. Have you understood? That's the structure of an antiform. Convex upwards, the dips away from each other, and if I draw the line here, then this is what it is all about. The dip is this way, dipping away from each other. But what is a syncline? How will I draw a syncline? What is the characteristic of a syncline? The older rocks in the syncline, the older rocks are at the flanks. So, we have old, young. Young, old. So you have old, young, old. So if you have to have a synclinal characteristic, then the older rocks has to be at the flanks. And the younger rock has to be at the core. But it has the shape of an antiform. So this is what is called an antiformal syncline. But what you see essentially here is something very, very interesting. And that is, here you see the stratigraphic succession has been inverted. So essentially, this is the similar like an antiform, but stratigraphically it has the characteristics of a syncline. And this, if you have to combine the two, then the only option is that your stratigraphic sequence of the folded layer, the stratigraphic sequence of the folded layer has been inverted. And we know from our previous studies that then therefore this is one fold, but previously something had happened, either faulting or folding, let's say folding, where earlier normal layers were inverted. So this would mean that there was a folding before this folding. So essentially, this cannot happen unless it is refolded. Unless this is refolded. So that means there has been a fold before which inverted the limb, and then the inverted limb was folded as an antiform. So this is what is called an antiformal syncline. Have I got it right? Okay. So now, like, you can well imagine if there is something like antiformal syncline, so you will have a synformal anticline as well. A synformal anticline as well. Now let's see how this works. Like before, it will be a synform to start with. It will be a synform to start with. So here it will be a synform. To start with, it should have a synformal structure. That's for sure. It will have a synformal structure. That means the dip is towards each other. Here also you can see the dips towards each other. And it has a convex downward shape. That is the classic case of a synform. Not syncline, synform. But it says it's an anticline. In anticline, the older rocks occur at the core. The older rocks occur at the core. So we have old, young, 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 old, old, young. Once again, here you have the characteristics of an anticline. And what is that? That the older rocks will occur at the core of the fold. So here I have older rocks occurring at the core of the fold. If I translate this here, you can see the older rocks are above the younger rocks, same as here. The older rocks occurring here. That means here also, if you have synformal anticlines, that means that before this folding, there was an event, folding or faulting, whatever it is, that there was an event that predated this folding, or that folding happened first, which caused the inversion, and then that inverted layer was formed. That makes synformal anticline. So this is very, very important to realize that synformal anticlines and antiformal synclines essentially indicate stratigraphic inversion. There is no other way you can work around the problem if you get such a feature. There is no other way in which you can get around this feature. So this is what is about inversion of stratigraphic sequences due to folding. Right? So now I think I have given you a reasonable first order description of folds, how they look, some of the important connotations of it. But I think now we need to switch over to something called faults. We need to find out a little bit of faults. Okay? So, we start with this. Now, from our previous lecture, this is, let me also just tell you another thing before we move into folds and parts. A few things I think I should tell you. Say, for example, I have a layer where there is pure shear. Remember, pure shear, and this is extension. So I guess what we can do is this we can call as sigma 1, and this is we can call as sigma 3. This is the shortening direction, and this is the ending direction. So what happens when there is shortening here and there is stretching here? Somewhere there will be two lines where you will move from shortening to extension. There has to be a zone where there is no finite strength. No finite strength. And there will be two such lines oriented at around. This you should know from your basic engineering that you start learning. These are the zones of shortening. And these are the zones of elongation. These are the zones of elongation. So here, if you have something, it will be stretched. And here, if you have something, it will be shortened. But if you have something here, then it will undergo no deformation at the moment here. But as you know, if sigma 1 goes on increasing, then this distance will be shortened and this distance will be stretched. So what happens? From a sphere, you start to get an ellipse and then ellipse. This is what is happening. This is a ellipse. This is if you apply sigma 1. So this is sigma 1, this is sigma 1, and this is sigma 1. So what is happening as you're increasing the sigma 1 this distance, the mass remaining constant, the elongation becomes more and more. So what happens? These two lines start to move at a low angle. So these are called instantaneous zones of no finite strength. Instantaneous. They can rotate if the amount of pure shear increases. But before we go into this type of progressive deformation, etc., let us look at here. Say, for example, if before this strain was applied, let's say, before this strain was applied, let's say there was a dike like this, say D1, and a dike like this, say a body like this is D2, and another body like this, which is, say, D3. Right? So, when you apply the strain fields, what happens is, this D3 does not undergo any change. This D3 does not go any change if it was parallel to the zone of no finite strain. It will undergo no change. But D2, this will be in the zone of elongation. And this is the zone of shortening, this is the zone of shortening. So it's in the zone of elongation. So what will happen to D2? D2 will experience this is what will happen to D2. So this is what is called necking. Necking. And this is what happens. So the mass flows into this direction. The mass that you lose here flows into this direction. So these are thicker, and these are thicker, and these are thicker. In the extreme case, what happens? These are detached. Have you understood? These are detached. Now these are called budines. These are called budines. Have you understood? These are called budines, where you have this necking here, and once the extension becomes higher and higher strain, then it rips apart from here because of necking, and this forms budines. Normally, budines form in more competent layers. Rheologically competent layers undergo budinaging, whereas the incompetent layer around the budines, they flow. They just keep flowing, flowing around the competent budine layer. Because the budinage cannot flow, because it's very strongly competent, so it tears off. So you produce budine, these are called budine necks. These are called budine necks. So this is where it was essentially torn off. So this is what happens to D2. If it's in the zone, if it started to be in the zone of elongation. But what happens to D1? D1 is in the zone of shortening. You see, D1 initial orientation is here. So it's in the shortening field. And so what happens to D1 is the following. It undergoes folding. It undergoes folding, and the axial plane of the folds. You know, this is what is the axial plane of the folds. So the axial plane of the folds are essentially like this. And the body, and you find the budines, these are folded. So depending on the initial orientation of bodies in the strain field, and where you have domains of elongation and shortening, the initial orientation dictates what type of folding you will, what type of deformation, or what type, how its morphology will be once you apply the strain to it. The initial orientation is very, very important. If they are oriented parallel to the zone of no finite strain, they will experience no folding. But those which are in the elongation zones, they will undergo necking and eventually budinaging. So, in the budinages, the incompetent layer simply flows around it. The incompetent layer flows around it. And you see there is no folding except in this part. This is called bending folds. These are called bending folds, which happens at the necks of the buddings. So here you have necking, and here also the external foliation will flow like this. But here, where the budding is, you will see this goes inside, and you have sort of a bending fold. But they are large wavelength folds, very large wavelength, small amplitude folds. But this is not the case if you are here. This will undergo folding. Have you understood? So essentially, this is something very interesting that happens. So initially what happens in the shortening field for D1, initially it will fold like this, broad open folds. And once you increase the strain, then these layers will fold like this. And when you do this, these layers here, first these layers were oriented like this at high angle. But what happens due to intensity of deformation becomes strong shortening. This fold limbs, you see, the fold hinge becomes thickened and the fold limbs become thinned. And this way, when this fold limb is oriented parallel to the zone of extension, then what happens is, even in this folding, you generate buddings. This is what happens from here to here to here. So what is happening? Initially, the fold limbs are at this angle, which is within the shortening field. So it continues to shorten. But when the intensity becomes so high that it becomes oriented parallel to this, then these limbs and these hinges starts to behave like D2. Do you understand? So what happens? The limbs become thinner and necked, and the hinge becomes longer. Ultimately, the limbs become detached from the hinges. So these are called rootless folds. Rootless folds. That means only the buddinaged hinge part remains. The other parts are all buddinaged. So what happens? This is a classic example where folding occurred initially, and the layers were at high angles within the shortening field, so they continued to be shortened. As it became shortened, the folds became tighter, and as the folds became tighter, they fell into the direction of elongation. So if it bends to the direction of stretching, then they will behave now like D2. So what will happen? Different parts of the fold will become detached, and you will have buddings. The limbs will become buddinaged. You will have bending folds. You will have necking, and even the hinge part will be detached from the main body, giving you what is called rootless folds. Rootless fold. That means it is no more connected to the limb. So what I was trying to say is, the important point is, the initial orientation of a particular feature in a strain field is very, very important. It's very important whatever happens in a strain field. The initial orientation is very crucial. How it was before, but as the strain, you must understand, but this is only true for some time, because as the deformation progresses, especially in the shortening field, and when the intensity becomes higher, then of course the initial this thing is lost, and the deforming fold, when it becomes parallel to the elongation, then everything is buddinaged. This is very, very common and is called partly as progressive deformation. Part of a progressive deformation. That means there was a progression of deformation where the intensity increased. What happens if the intensity decreases? That's a different question. But with progressive increase of intensity, what happens is initial folds become buddinaged. Here, if the original orientation of D2 is here, there is no folding. There is no prior folding. you won't get a rootless folding shear because there was no folding to start with. But here in the shortening field, it becomes more complex, especially because these two zones of no finite strain starts to move away from each other here, for example. So this becomes the zone of elongation or zone of stretching. So very, very complex fold structures develop, but at least in the initial stages, the initial orientation becomes very important. Even this one, D3, as I told you, at the initial stage it may not deform, but as you increase the strain, you can see this moves off. So, your strain field becomes off. So this gets into the shortening field. And once it gets to the shortening field, it will fold. It will fold. Initial orientation was here. But when you increase the strain, it is at the same orientation, the zone of finite strain. But the zone of no finite strain swings away. And this, when the zone of no finite strain swings this way, then it gets into the shortening field. So this will also fold, but a later part of the folding event. Later part of the folding event. So deformation makes things very, very complex. Now I have drawn this. I have drawn this for pure shear, but the whole logic remains the same. Even if I consider, say for example, a simple shear component, whereby a sphere becomes like that. So this is like that. So now, this is sigma 3, the stretching direction or elongation, and this is the shortening direction. This is sigma 1, which is the shortening direction. So now what happens? The same thing applies. Here you see, you have this zone of no finite strain. So what happens is, everything remains the same. Most of the things, dominant things, remain the same. Only thing, the orientations are different. The orientations are different. Have you understood? The orientations are different. But essentially, most of the things that I have told you here remains the same. Only thing, here, the ellipse continues to rotate. Ellipse continues to rotate as more and more shear is applied to it. So, it continues to shear. And the zone of maximum finite strain and sigma 3 starts to rotate. I told you, simple shear is essentially a feature that involves rotational shears, where the sigma 1 and sigma 3 with respect to a georeference frame moves. In pure shear, sigma 1 and sigma 3, the orientations does not change, the magnitude changes. But that's why it's called irrotational shears or non-rotational deformation. But in rotational deformation, where it's simple shear models, there the axis rotates. The axis rotates. Remember, this is sigma 1, sigma 3, and this is the intermediate one. This is called sigma 2. So we have sigma 1, sigma 3, and sigma 2. Before we wind up, there is an important thing that I would like to tell you before we prepare for the last lecture of this thing. I'm just giving you the essential parts. I'm doing it with respect to a simple shear. Simple shear. Here the rotation is clockwise. Here the rotation is clockwise. So from the left you go to the right. That means this is called a dextral shear. If you had, this is called dextral. And if you are here, this is sinistral, because essentially you're moving from right to left. So it's called left-handed shears, and this is called right-handed shears. So using the term sinistral and dextral. Now, so this is the stretching direction. As you can see, this is sigma 3. I'm not writing the direction, I'm just saying this is sigma 3 and this is sigma 1, which is this direction. This is sigma 3 and this is sigma 1. And you know this point here and this point here, this is sigma 2. So you remember, this is sigma 2. This is sigma 1. This is sigma 1. This is sigma 3. Here it's elongation and this is shortening. Now you see, normal faults are normally found here. This is the zone where you find normal faults. Are called reverse faults. These are called reverse faults. And here you find what is called regarding fault planes here, what you see is this is the orientations or normally of the normal fault. I have drawn it, does not mean it occurs here, it can occur anywhere. The question is, this is what is where the normal fault. So normal faults normally are perpendicular to the stretching direction, perpendicular to sigma 3, generally normal faults. And sigma 1, which is the shortening direction, normal faults, since they are perpendicular to sigma 3, they are parallel to sigma 1. Have you understood? And reverse faults, I told you about reverse fault, we will recap that again. The reverse faults, where the hanging wall moves up related to the footwall, and normal faults are where the hanging wall falls down with respect to the footwall. Those faults essentially for normal faults, these are normal faults. Normal fault forms perpendicular to the stretching direction, and that is parallel to the shortening direction. Normal faults. And reverse faults are perpendicular to the zone of shortening. That means reverse faults form parallel to the elongation direction. These are the two reverse faults. And these faults, I will just name it, we will see it later. These are called strike slip faults. We will talk about it a little bit later. These are called strike slip faults. There are two pairs of strike slip faults. Here, this is also a strike slip fault. But there are two names to it. Here you see the fault orientation is like this, and here the fault orientation is like this. You see, this one is like this. So here, the movement direction at the top is the same as this. You see, this is moving this way, this is also moving this way. So this strike slip fault is called synthetic. That means the movement is in the same direction. But if you look at this, it is different. These strike slip faults are called antithetic faults. Antithetic faults. That means the movement direction is opposite of the shear zone, opposite of the strain field. So you have two sets. This is the fault structure generally. Very simply, these are the general strain fields for fault structures. One is the normal faults, perpendicular to the extension direction, stretching direction. That means parallel to the shortening direction. Reverse faults are perpendicular to the shortening direction, and that is what parallel to the stretching direction. And then you have two sets of a conjugate faulting. in this, you can see since you're pressing this whole part moves this way, and here you're pressing this, so this part moves this way, so you generate two sets of faults. This is one set of fault, which is, you can see here, and one set of fault here. This is sinistral and this is dextral. No matter how you see it. This is sinistral, this is dextral, and this is sinistral. Now this sinistral fault, the shear sense, the movement sense, the top to the right, the top to this part to the right is the same as the movement direction of the shear plane. So this is called a strike slip fault. Strike slip fault. Sorry. It's called a strike slip fault. Not strike fault. Strike fault is a completely different thing. Strike slip fault. Sorry. Strike slip fault, and this is called synthetic strike slip fault because the movement direction of this and the primary shearing sense is the same. And these are strike slip faults. These are antithetic because the movement is this, but this part is moving this way. So these are called antithetic shears. So you produce a conjugate shear, conjugate planes, where the movements are opposite in the sense they are sinistral and dextral, or in the sense they are synthetic and antithetic strike slip faults. And you have normal faults and reverse faults. So in the next class and the last class, we will talk a little bit about faults.